So we just talked about average power for sinusoidal voltage waveform, and we showed using the trig identity that the average power is going to be half the maximum power. Sometimes then we can describe a sinusoidal waveform by its effective voltage, VRMS. And root mean square averages applies to voltage or current waveforms sometimes. We don't talk about RMS power. We talk about RMS voltage or RMS current. Okay, and since power for voltage, power say across or dissipated by a resistor, goes as the square of the voltage, if we want to relate voltage to power, we need to talk about the average of the square of the voltage. That would make more sense. But if we still want to have units of volts, not volts squared, we can take the square root of that, and that will be our VRMS. Okay? So procedurally, if you're given a waveform, a voltage waveform, you would first sketch V squared, then you would compute the average V squared in the same way you compute the average power, that is by looking at the area in one period and divided by the period, and then in the end you would take the square root of this value that you found in part 2. Okay? So what would it look like for different types of voltage waveforms? Oops, that's too far. All right. So if we have a sinusoidal voltage waveform, A times sine of 2 pi over big T times T. T is the variable of time. This is variable. Okay, let me pick a different color. And this capital T is the period here, as you notice. By the way, this 2 pi over T is sometimes called omega, just to connect it to the previous part of the video. So if you do that and calculate the voltage, the RMS voltage, you will find that VRMS is V peak, and in this case it's A divided by square root of 2. Okay? So remember, the average power is just peak power divided by 2. So if you think about it, it would imply that the RMS voltage is peak voltage divided by square root of 2. So in this case, it would be A over square root of 2, right, for the problem above. Okay, so if you had a voltage waveform that looked like a square wave, if you plotted this, you would get A squared if you plotted this, if you used the procedure and plotted the square of the voltage waveform, A squared, and if you calculate it in one period, the area under A squared, you would just get A squared times T on. That's the time that the voltage is on. And then, if you recall, you need to divide by the period, by T, and then you would take the square root of that, and that would be your VRMS. Okay, so VRMS would then be A, the magnitude of the voltage waveform in volts, times the ratio of the on time to the total period. And sometimes this ratio is called the duty cycle. Okay, so it would be the peak voltage times the square root of the duty cycle. All right, so VRMS is the effective voltage. The that if it were constant, it would deliver the same power as the waveform that we're talking about. So that's why when we talk about the wall power, when the wall outlet voltage, we sometimes say 120 volts. That is RMS. Okay, so for outlet, VRMS is 120 volts. That's in outlets. That's in the US. All right, different countries have different standards. In Europe, the RMS voltage is 220 volts, for example. Okay, so you can answer the questions. What is the average power absorbed by the light bulb? And we already calculated that previously. If you recall, that was just 60 watts in the previous video. And we actually don't need to use RMS. But now we can use RMS to calculate it as well. And how would we use that? For 170 volts, you'd divide by square root of 2 and get 120 volts or so RMS voltage. And then you could just say that power equals VRMS squared divided by the resistance. And you'd get the same value, 60 watts. All right, so question 9 is a kind of conceptual qualitative question. What happens to power and VRMS when the T on, for right now we're talking about this square wave, when T on is halved, okay, so goes down by a factor of 2, okay, while the period is not changing. Well, if we're applying a peak power for half the time, then we would get half the power. So as far as the power is concerned, it would only be half. But what about VRMS? VRMS goes as square root of the power, so that would go down by a square root of 2. So for VRMS, that would go down by 1 over root 2. And for the power, that would go down by a factor of 2. Okay, power, factor of 2, VRMS, factor of root 2. Okay, so you can think about it some more. All right, the last slide actually in the notes had something to do about reactive power, and we'll talk about it later. Okay, so later we'll discuss this. And actually the question really should have been for a waveform that's shifted, the current waveform that's shifted by a quarter of a period with respect to the voltage waveform. Okay, so it would look something like this. Not like this, but like this. Okay, quarter waveform off. And we'll talk about it a little bit later in the semester. Okay, so this wouldn't happen in a resistor. In a resistor, the current would always be proportional to the voltage. And if the voltage is sine 2 pi over big T times T, then the current would just be 1 over R times that. All right. Okay, you can also read course notes on the website to supplement your understanding of VRMS. But that's it for now. Thanks.